But also, you got always.
I will begin with a word of prayer. Ahem. Hey, another use. What do you know? I will begin with a word of prayer. So, dear Father, we thank you for this day. I thank you for these students, most of them, and we just pray that you be with us today. Help us to glorify you in what we do, and just to learn a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. So, what, did I say something? Wait, I didn't bring my glasses, but I feel like there's some people here that aren't usually here. Is there CFA people? Ah, there's one. Are you enjoying being singled out in all your classes today? Is everyone singling you out in all the classes, or just this one? Just this one? Okay. Don't worry, we welcome visitors, unless they're parents, in which case, get out. Just get out. No. Parents are the worst, right? No. Just kidding. They pay the bills, right? Okay, so today I want to talk to you about momentum. So obviously potential energy, conservation of energy, very useful as we've seen, right? I would point out I covered a pretty wide swath of examples in class, but there's more in the notes. All right, so if you look at the lecture notes that I've provided you guys, there's a number of examples in the lecture notes that I've yet to talk about in class, so maybe I'll circle back to those next week. Who knows? But like there are examples in the lecture notes about pulleys, or a mixture of like an inclined plane and a pulley. I have the potential energy for a seesaw is another thing that's in the notes, which I haven't talked about in class. But anyway, let's get started on this. So I'm going to start by talking about momentum for a point mass. All right. So let's begin with that. So what is a point mass? If you have a point mass, in other words, a mass where we're not really concerned with its dimensions or anything like that, with velocity v. Velocity is a vector, right? Then this has momentum p, which is a vector, and it's equal to m times v. All right? So momentum is the mass times the velocity. All right? So at first glance, you might be like, well, we already know mass, we already know velocity. How does this help us? Well, it does. It does. It actually helps us quite a bit in terms of the concept. Now, so before I get any further, what are the units on momentum? So let's see here. The units on momentum are going to be kilograms times meters per second. All right, so that's the units on momentum. You know, I don't know, I think it always kind of amuses me that we have no special word for the unit on momentum. Like, you know, the units for energy, right? Newton meter, we also call it what? It's a joule, right? This is a special name. Or Newton, right? Newton's a kilogram meter per second squared. That's got a special name. But momentum, no name, just kilogram meters per second. So anyway, it's kind of I don't know why. Why did momentum not get its own special set aside name for that combination of the units? I don't know why, but anyway, so look at Newton's law. Let's look at Newton's second law. All right, so in this case, for a point mass, what do we got? We have the net force, right, is equal to the mass times the acceleration, right? But the acceleration is dv dt, right? And for a point mass, what's the deal? Well, the mass is not changing, right? So we can bring the mass inside the derivative, and we have mv, right? But what is mv? Well, mv is the momentum, right? So this is exactly the time rate change of the momentum. So this is dp dt. So this is interesting. Apparently Newton's second law can be restated as the net force is the change, infinitesimal change in the momentum with respect to time. Now, oftentimes, we're interested in something called the impulse. So let me define impulse for you guys. Impulse is a special word we use for the change in momentum. All right, so the impulse is the change in the momentum. And the symbol typically used is J. And J is equal to the integral from t1 to t2. So if you're talking about impulse, it has to be with respect to some duration, right? With respect to some time interval. So say t1 to t2. And so that's going to be, well, you integrate the, to find the change in the momentum, you integrate the change, right? So this would give us the change in the momentum. But what else could you say? Right? Well, that would be the integral of the net force, wouldn't it? So alternatively, you can define the impulse as being the integral of the net force on the particle. So the impulse delivered to the particle will be the time rate, and the integral over time of the net force. You can say that. All right. Another thing I should mention is that we can write kinetic energy in terms of momentum is kind of neat. So let me just point out something to you guys. If we do v squared, what's that equal to? What is the speed squared in terms of a dot product? It's what? It's v dot v, right? So can you tell me how that would be in terms of momentum? How do you get the velocity from the momentum? How do I solve this for v? V is what? 1 over m times p, right? So plug that in over here. We've got 1 over m v dot 1 over m v vector. And that gives me v dot v. Oh, my bad. I was supposed to put p there, right? Sorry. So that gives me, excuse me, p dot p over m squared, right? So in other words, v squared is equal to p squared over m squared, yeah? This isn't really surprising, right? Because if you look at this, if you look at this equation right here, this one right here, if you just take the, the magnitude of both sides, this immediately gives you the magnitude of the momentum is equal to the mass times the magnitude of the velocity. So if you wanted to get the magnitude of the momentum, you just take the mass times the speed, right? So fine. So v squared is p squared over m. So what's the formula for kinetic energy then? 1/2 mv squared, right? But what is it now? 1/2 m p squared over m squared, right? So the formula for kinetic energy in terms of momentum is exactly p squared over 2m. So there you go. There's a formula for the kinetic energy in terms of momentum. This is useful, all right, because we'll work problems where we calculate the momentum, and if we know the momentum and we know the mass, we can find the kinetic energy. So that's nice. Okay, so far this is all three-dimensional, right? It's all three-dimensional. Let's drop back and talk about one dimensions for a second here. So one-dimensional case. In one dimension, we have additional tools to understand the integral, right? So, for example, what happens if I tell you that we're given the graph, right? And I'm going to give you a graph of force as a function of time, and we're going to put this in terms of seconds, all right? And I'm going to put this in terms of newtons, all right? But I'll use numbers, so I'm going to suppress the units for the sake of not like cluttering up the math so much. It's always a battle for me whether or not I should write out units on these kind of problems. But suppose the graph of the force as a function of time looks something like, oh, I don't know. Let's say this. All right, so here's times 0, and let's say over here is times 7. Okay? And furthermore, I tell you that you're given that the momentum at time 0 is equal to, let's say, 3 kilogram meters per second. Who is clicking? I keep hearing clickety, clickety, clickety. It's probably you. I usually can't hear myself in here, but anyway, so suppose I give you an addition that this area, the area of this loop right here is maybe 4, and the area of this one is, 2. So let's suppose that's given. If I had it on graph paper, you could figure out those areas, right? Like problem 1 on your next mission, I give you a graph of force versus time, so you could actually calculate the area by counting up the boxes, right? So my question then is, what is P of 7? Whoever is clicking on the keyboard needs to stop. Thank you. So what can we do? How can we solve this problem here? Well, let me show you. So what we do is just use Calc 1, right? So like the integral from, say, times 0 to times 7, right, of the force with respect to time is equal to what? It's equal to the change in momentum, right? So it is literally equal to the integral from 0 to 7 of dp dt, right? So the net change theorem gives me P of 7 minus P of 0. So let's see here. And what is this area? Can you tell me? 2. So, and you got that from 4 minus 2, right? Because we have 4 positive area, 2 negative area, right? It's the signed area we're calculating. And so 4 minus 2 is equal to P of 7, which we were trying to figure out. And P of 0, what was that? I gave that to be 3, so minus 3. So what's P of 7 equal to? 2 plus 3, right? So we get 5. And there you go. Now, of course, what I mean by that, I try to put, I always feel guilty here for not putting units in the answers. So that is, of course, 5 kilogram meters per second for this problem. All right. So if you're given a force versus time graph, you can figure out the change in momentum from something like that. All right? Example 2. You can say, what's the average force on ball? And so we can imagine a situation where the ball comes in here like this at, say, I don't know, let's say 20 meters per second, right? And just for the sake of convenience, I'll make this a pretty heavy ball. I'll make it mass equal to 2 kilograms. I mean, that's ridiculous, but just for the sake of the calculation. So suppose you have a 2 kilogram ball. It comes in and it hits the wall. It's a very strong wall. It rebounds, right? It rebounds, it bounces back. And let's suppose it rebounds with 15 meters per second. So it loses some of its energy, right? So here we go. It comes in, hits the wall, comes back right there, okay? So my question is, what's the average force exerted on the ball during this process, right? Well, let me not ask that. Let me ask a different question. What's the impulse to the ball in this process of the collision? What's the impulse going from here to here? What's the impulse? So the change in momentum is what? So we've got, 2 kilograms times 20 meters per second, right? That's the, that's the initial momentum. I want to put the final one first, right? So change is final minus initial, right? So PF minus PI, which in this case is, the final momentum is minus 15 meters per second times 2 kilograms. And then we're doing minus 20 meters per second. I don't know why I wrote the V first, but multiplication commutes, so it doesn't matter, but let me put this hideous thing away. There we go. So this is the impulse delivered to the ball. So what's the impulse here? You've got 30, you've got 40, so minus 70 kilogram meters per second. Now, does the sign make sense to you? Why is it negative? The impulse over the rebound of the ball. Yeah? Right, it's going in the direction away from where it was started. That's a good answer. So it's because I'm counting left as negative here and right as positive, right? So the change in the momentum is to the left, which is why the impulse is negative. Now I'll ask the question, what's the average force exerted on the ball by the wall, right? Now that question only can have an answer if we tell the time scale, right? How fast the rebound happens will inform how big that force was to make this change happen, right? So let's suppose that it happens over 1/10 of a second. Suppose, rebound over a delta t of 0.1 seconds. Then the average force then would be, of course, delta p over delta t, which in this case would be minus 70 kilogram meters per second divided by 0.1 seconds, which would then give me minus 700 kilogram meters per second squared, which of course we know is a Newton. We got out of the way here. So to illustrate, I brought my gun. Now, fortunately, it's not 2 kilograms, right? Like it's slightly less. Ah! Ha-ha! But, and also I think that I don't think this is losing, from the look of it, it's not losing, 25% of its speed in the collision either, is it? It's pretty well, I would say it's close to an elastic collision with the wall. What's an elastic collision? What's that? No deformation. I think no deformation is a characteristic of elastic collisions. That's not the definition, though. So the definition of an elastic collision is a collision in which the kinetic energy is conserved. Kinetic energy before is the kinetic energy after, right? So bouncy collisions tend to be elastic, but you're right. If there's a deformation, like if two cars come and collide into each other and then get mangled and skid off, that's a pretty inelastic collision, meaning kinetic energy is lost in the process. All right, so in order to talk about the problems I just mentioned, like two cars coming together, we need to talk about another concept which we haven't talked about yet, and that's the center of mass concept. So let's get to it. So what I want to talk to you now about is a system of particles. All right, so a system of particles. So let's imagine you have n masses, all right? 1, 2, 3, 4, all the way out to n of them. And let us work out what's called the center of mass. Now, the center of mass is sometimes also called the center of gravity. In terms of application, the center of mass of an object is like its balance point, right? And so we'd like to understand how that works. And so unfortunately, I was looking through my notes, and this is just not in the notes, by the way, guys. Like if it's in the lecture, I couldn't find it, so one of those places where there's an oversight in my currently published PDFs, so make sure you get these things down. So I want to talk about system of particles. So we're going to put m sub I at r sub I for I equals to 1, 2, 3, all the way out to n. All right? So I'm saying that these are the positions of the masses with respect to some fixed inertial frame of reference, right? So like here's a picture of it. Here's my origin. And let me just draw some position vectors with my ghostly green marker. So here, I don't know, here maybe, here, here. I'll do, so so like this is going to be R1. Here's the position vector R2. Here's the position vector R3. Here's the position vector Rn. All right. So I'm saying you've got mass 1 out here. Mass 1 is here. Right? Mass 2 is here. Mass 3 is here. And here's the nth mass down here. All right? And so we're thinking of this as a system. And so what we're going to do is we're going to write down Newton's laws on each one of these masses. All right? So to do that, what do? Newton's law for each mass, right? How's it go? So what you want is you want m1 times a, the acceleration on the first one, right? Which of course would be what? This would be equal to the sum of the what? Sum of the forces, right, on what? On m1, right? So we do sum of the forces on 1. Now I can break that up. What are the forces on m1? So the forces on m1, there's a few different things going on. First of all, there's what I might call an external force. So there's an external force on 1. All right? But then there's also forces which are not external. There's forces that could be, say, from the gravitational interaction of mass 1 and mass 2, or perhaps from the electrostatic repulsion of m1 and m2. Other forces that are so-called internal forces, forces that are between the masses. They're subject to some sort of interaction between the masses. So like, here's my notation. I'm going to call this one the force. This is the force of 2 on 1. All right? There would also be perhaps a force of 3 on 1. There would also be, and so forth. There would eventually be a force of n on 1. So you've got all these different forces. You've got the external force, which is from whatever action, whatever's from outside the system that acts on the first mass. And then you have all of the, you know, the whatever internal forces you have from the masses pulling on the first one. So what that looks like is this. You have the external force on 1. It's a vector. And then you have plus, I'll write it as a sum. Basically, it's the sum I not equal to 1 to n of f, and my notation that I'm using here is I, comma 1. And we can replay this this story again for the next mass. All right. So like here, you have the external force on 2, right? And then I want to point out something. How about this? What's the force of, what's the net force of mass 1 on mass 2? How does that have to go? This would be F1 on 2. How are these two forces related? They have to be equal and opposite. They have to come in third law pairs, right? Newton's third law says that the action is equal to the reaction, right? So these internal forces have to be balanced in this way. That's going to be important in about 5 minutes or, well, about 2 minutes. So we've got this one, and of course, you know, there's also this force of 3 on 2, and so forth. You got the force of n on 2, right? Do you want me to write the picture for each mass? So I can keep going here. Down here, you've got the external force on the nth one, and you've got, you know, oh man, my color coding is slipping. You've got the force of 1 on n. You got the force of 2 on n. and so forth. The force of 3 on, I'm just drawing this many. All right? Okay, so what's next? We have M2 rather, A2 is equal to, and I'm just going to, the sum of the forces on M2, right? So what is that? That's the external force on 2, plus this time we have the sum I not equal to 2 on N. Any questions about that? So I usually tell this story at this point. When I took junior level mechanics, well, actually I didn't take it. I was there for a day and then I got kicked out. Because the professor I wanted to audit it, and his condition for auditing was I had to do all of the homework and get a C, otherwise I would fail the audit. And I'm like, but that's just take what? So I gave up on auditing it. But the day I was there, some student was debating, why can't a mass put a force on itself? See, because that's what I'm not including in here, right? What's the force of 1 on 1? What's the force of 2 on 2? What's the force of 3 on 3? How about those internal forces, right? They're not present in what I'm writing. And so the way he explained this was the following. He's like, well, if you think you can put a force on yourself, by all means, he's like, you take your hands, bend down. I probably can't do it. Put your fingers under your toes and pull yourself off the ground. Just lift right up there. So, no, we can't put a force on yourself. So, which then precipitated some discussion about punching yourself in the face, but anyway. Okay, so moving on here. We can keep doing this, right, for each one of the masses. And so if you don't mind, I'm just going to skip ahead, ... Mn An is equal to, well, the external force on the nth one plus the sum I not equal to n of f I comma n. All right. Now, you guys tell me, what could I have written here in each one of these? What should I write? How about this? This is what? This is really the time rate change of the momentum on mass 1, right? So this is dp1 dt. Agree? I mean, we just learned this about 10 minutes ago, but there it is, right? The time rate change of the momentum is equal to the net force on 1. And you can do this for 2, right? And if you can do it for 2, you can do it for n. So there. Now what we're going to do is we're going to just add all of these equations up, right? Just add them all up. What happens? Well, when we add the derivatives of the momentum, we get d dt of what? The momentum 1 plus momentum 2, right? Plus the nth momentum. And what's that equal to? Well, it's equal to the sum over I equals 1 to n of the external forces, right? So this is the total external force, right? If we just add together the external force on each mass and add them all up, that's the total external force, right? And then you have plus the sum j equals 1 to n of the sum of I sub j not equal to j, I suppose, to n of f sub I comma j. Listen, you don't even need to write that down. Think about it. What happens as you add up all those internal forces? I saw some people going like this, yes, right? There's third law pairs. Every internal force in here has a pair, a partner, equal and opposite in direction. As you add these up, this collapses to 0. So we have this beautiful result right here. This is the net external force, which we could just call this the external force on the system, right? And we're going to call this the net momentum. So what we have here, as well, I'll explain more fully here in just a second, is that the time rate change of the total momentum for the system is just equal to the external force on the system. Now, I haven't quite earned the right to write that boxed equation yet. Let me explain to you why. Because I need to tell you what, I mean, let me complete the story here. So what is the center of mass? What is the center of mass? How do we define center of mass for this system? So, definition, yowzers. The total mass, big M, is just going to be the sum of the masses. All right, total sum of the masses. The center of mass is, well, it's the weighted average. But, you know, if you want me to make this actually a weighted average, I have to, like, put in some G factors in here, right? Because at the moment, if these aren't weights, these are just masses, right? Sorry, that's a horrible physics pun. But I stand by it. If you want me to write this as a weighted average, I can do it. Just give me a second here. Here's this as a weighted average. And I will admit, although my current purpose for this is mostly to make a stupid joke, this actually does have a use, because if you want to find the center of mass, you could also find it by, you know, essentially averaging the weights. You know, doing a weighted. This is literally a weighted average, because mg is the weight, right? So the more heavy a given mass is, the more it figures into where the center of mass goes, right? That's how this works. But once you have this, well, if that's the center of mass, right? What happens when you differentiate this? What's you know, let's say big V is dr dt. This will be the velocity of the center of mass. What's that going to be equal to? See what happens when you differentiate this? You have 1 over m, which is a constant, right? And then you get m1. Well, what's dr1 dt? dr1 dt is just v1, right? Where I just noted that, you know, dri dt is equal to the ith velocity, right? So the velocity of the center of mass is likewise the, you know, the weighted average of the velocities of the masses. And of course, then we define, this is the definition, okay, guys? This is also a definition. I'm defining big V. The definition of the big momentum is the total mass times the velocity of the center of mass. So big P is the total mass times the velocity of the center of mass, which is literally equal to what? See these cancel? And you get what? You get m1 v1 plus m2 v2 plus plus mn vn, which is what? So maybe you can recognize that this is literally P1 plus P2 plus Pn. So the net momentum, the momentum of the system is the sum of the momentums of the constituent masses. So what does all this mean? This means that if we have a system of n particles, right, and we want to think of it collectively, we can ignore essentially the internal forces, right? And we can treat it as a system where the force on the, you know, system is just the sum of the forces on the constituent masses, but it's as if that system was a single mass, big M, right? Which is at the position center of mass, R, with velocity big V and total momentum P. So this allows us to treat systems of particles as if they're just a single particle. This is, you know, really how we think about everything, honestly. We've been using this idea even before we did this derivation for sure. Now, so what's a collision then? Once we have all this, we can start talking about like what's a collision. We can start applying this idea, these ideas. So what is a collision? So a collision is basically when you have some system of masses which, well, I know this seems a little bit circular, but forgive me, collide. On a small enough time scale that the external force is negligible. In other words, the collision is happening fast enough, all right, so that there's no time for any external force to change the momentum of the system. All right. So let me just be more specific here. Example, what am I on? Example 2, 3? I can't remember. This feels like example 3 because I did the silly gun thing, didn't I? So I guess, well, here we go. Let's put a car here. And let's put a bus here. All right, we'll give the car, you remember my numbers. We will give the car 30 meters per second as its velocity. And we'll let its mass be 2,000 kilograms. There we go. The bus, we will make it go a little bit slower. We'll put it at 10 meters per second. All right. And this is going to be a 6,000 kilogram bus. All right. So the car and the bus, they collide. All right. And they get stuck together. So it's definitely not an elastic collision, right? So here, so you got the car and the bus, they're all intertwined car bus. All right, they collide, stick together, and then afterwards they go careening off in some direction, right? The moment where before they collide and then they collide, that's the process as a collision, right? If we're to study the motion of the car and the bus, what's actually going to happen is that what actually happens, of course, is that after they collide and they stuck together, then friction comes into play, right? The tires or whatever on the road slows it down, and it's going to kind of slowly slide to a halt. You know, that's what happens, right? And also, of course, I'm also being unrealistic in terms of, you know, let's be optimistic and suppose that the car would actually have, you know, applied the brakes, and the bus would have, you know, well, the bus isn't going to apply the brakes, bus doesn't care, but, you know, anyway, so maybe there'd be braking and other things, right? We're ignoring all that. Just hypothetically, maybe, you know what, it's at night, it's very dark. Oh, there's a thick mist. A ninja has put a thick mist over the realm. They can't see each other, so they just hit each other blindly. There's no time for braking or any of that stuff, all right? Fine. So then the question is, right after the moment of impact, how fast is the car bus going and at what angle? Okay, that's the question. So can you tell me what this angle is here? So in a problem like this, what you do is you use the conservation of momentum. We think of the system as being the car bus system, right? There's two masses involved, but the total momentum has to be conserved. Why? Why is the total momentum conserved? Because I'm saying it's happening over so short of time scale that the momentum is not changed, right? And if the momentum, if the short enough time scale that the momentum's not changed, what I'm saying is the external force is essentially 0 in the moment of collision. So dp dt is 0. The momentum's constant over the collision. All right, so let's call this one A. Let's label this one B. And so momentum conservation just looks like this. The momentum of A plus the momentum of B, right, is equal to, and we're going to assume mass is conserved here, all right? So mass of A plus mass of B, and well then times the velocity we don't know, all right? We don't know what this initial velocity after the collision is. We'd like to figure that out. It's not hard though, we can do it. So what's the momentum for A? Momentum for A is 2,000 kilograms, right? What's the velocity for A? Well, it's 30 meters per second, and it's horizontal, all right? What's the momentum for B? 6,000 kilograms, right? 6,000 kilograms times what? 10 meters per second, yeah? So I'm cluttering my equations with units again, right? There's another way to do this problem, which is to say I'm working in kilograms, meters, and seconds, and just omit the units until you're at the end. I mean, well, maybe I shouldn't do that. This is physics after all, but anyway. I forgot to tell you this semester, guys, but in calculus you should refer to me as Dr. Cook, but like in here you can just call me Mr. Cook because, I only have a master's in physics, so like technically I'm only a Mr. in here, So actually I don't care. You can call me Mr. everywhere. Certainly my college algebra students do, and I don't care what they call me. I just want them to shut up. Just stop talking when I'm confused, please. Anyway, it's an inequality. Like, inequalities never get easier, guys. Like, they're just that way, right? Like, if it's this way, it's one thing. If it's that way, it's another. And I sometimes just change it, and I don't see it. And then if you don't see it, it's really confusing. And they don't help you, because they're lost. And they'd rather be talking about how photomath is awesome. So, but anyway. So, listen, so what we have here is 60,000 kilogram meters per second. 60,000 kilogram meters per second is equal to, well, what's MA plus MB? 8,000, yeah? Kilograms times the initial velocity. So apparently my velocity right after the collision is in fact, 60,000 over 8,000 meters per second. 60,000 over 8,000 meters per second. So what's that equal to? $7,500? That seems wrong. I will trade your 7,500 for 7.5 meters per second. Just take a step back and think about that for a second. Like, you have the bus going 10 meters per second, right? You have the car going 30 meters per second. They collide, and then they're going 7,500 meters per second. That would be really cool. But anyway. I'm saying that partly to be humorous, but partly just as an advice on tests. Like, do take a second to think about your answer. Is it orders of magnitude off where it should be? But please giving me numbers. It's helpful. I'm not trying to. Okay, so there you go. That's the velocity. So what's the angle? Yeah, we shouldn't need to pick up a calculator for this one. So theta is 45 degrees, of course. So yeah, there's that. All right. So question. Well, a couple different directions we could go here. number one, how do you make this problem more maniacal? How do you make this problem more of a more annoying problem? Friction. Well, yeah, you could do that. You could say then, you could add the question, the coefficient of static friction is, or kinetic friction is whatever it is. How long does it, how long is it before it comes to a stop, right? You could do that. How would you think through that? So if I told you the coefficient of kinetic friction was like 0.5, yeah? What you would do is you'd figure out the initial kinetic energy would be based on this speed, right? Is this speed 7.5? You should tell from the inflection in my voice that it's incorrect. So no, it's square root of 2 times 7.5, so you're not going to give me any more numbers today, are you? No? Okay. Fair enough. I deserve it. That's good. It's good. It's good. So yeah, so you find the initial speed. That would give you kinetic energy. Friction is going to take that away, right? So to find out how far it skids, I would just set the initial kinetic energy right after the collision equal to the work done by friction over the slowing process, right? And the work done by friction over the slowing process would just be the friction force times the distance, right? The friction force in this case, assuming that we're on level ground and all that good stuff, the friction force would just be like the total mass times gravity times the 0.5 if the coefficient of kinetic friction is 0.5. So that times d would be equal to the kinetic energy. You could solve for d, find out how far it skids, right? And so if you're a forensic investigator and the coefficient of friction between tires and the concrete is known, then you can work backwards what the initial speed was before the two cars hit on the basis of how far the tracks are, the skid marks. So you can do stuff like this, right? Some people make a living arguing forensically like what happened before a collision, trying to trace back beforehand, right? That was actually not what I was thinking about, but thank you. I was thinking of something much more geometric, which is make this the road and make it go like this if this angle's given, See, because then you'd actually have to think about the direction of the velocity, right? What would VA be if that's the case? See, if that's 40 degrees, what's this angle here? If I gave you this angle, this would be 50, right? Because you can draw the triangle there, it'd be 50 degrees. And so then you would have used VA, would it be 30 meters per second. And then I want the unit vector in the direction of 50 degrees, which is easy enough, 50 degrees sine 50, you could do that. And you could work it out that way. So that would be different, right? Your initial momentum then for car A would have some vertical part. And it would, I'd have to run the numbers, but we could do that. That'd be a modification of this problem we could solve, right? The thing that's a little bit more interesting, if I still have a minute, I have 2. Yay. What happens with these when instead of having n particles, we have infinitely many? What happens? What happens to these sums when n goes to infinity? What do they become? So if n goes to infinity, and you don't want the mass to go to infinity, you think about these masses becoming infinitesimal masses. You think about them becoming dm's, right? So if you're adding together dm's, that's going to not be a summation, it's going to be an integration. So in the continuous limit, these summations become integrations, right? And so to find the center of mass for a continuous distribution of mass, we have to do an integration. If your object is one-dimensional, you've got a one-dimensional integral. If your object's two-dimensional, you've got a two-dimensional integral. If you got to do. If you've got a three-dimensional object, to properly find the center of mass, you're facing integrals over volume. All right. So we'll come back to that as we study physics. All right. Like I have one problem in your homework, which is about a one-dimensional object and finding the center of mass. So I'll try Monday to work a problem like that because it requires a conceptual adjustment of what we've done so far today. In other words, I'll actually make good on what the integrals look like for one dimension. I'll try to do that first thing Monday. So anyway, have a good weekend, you guys. Thank you to the CFAR for tolerating my harassment.